Good morning, students. Welcome to the class on NMR spectroscopy. We were discussing advanced topics in NMR spectroscopy. Now we will discuss about enantiotopic groups. Enantiotopic groups appear to be equivalent, isochronous, they are also isochronous, and give a single NMR absorption. So enantiotopic groups also, like homotopic groups, they will give a single NMR absorption both in proton NMR as well as carbon 13 NMR. But the only difference is when they are placed in a chemical chiral environment or when they are treated with a chiral reagent. So when we add a chiral reagent or when they are placed in a chiral environment, then only the enantiotopic hydrogens will give different signals. Otherwise, they will give their chemically equivalent, so they will give only one signal. I'll try to explain it with similar example because these two substituents are different. If we replace one of the hydrogen with some other atom, say for example I am replacing Ha with A, then it is a chiral center, right? Because this carbon is having 1 2 3 4 different substituents, so it is a chiral center. Similarly, if we replace Hb with another atom, then also it becomes chiral center. Now look at these two. These two are enantiomers. These two are a pair of enantiomers. So unless otherwise we place this molecule in a chiral environment, these enantiotopic protons are chemically equivalent, isochronous, so they will give only one signal. We will take the previous example and we will try to explain enantiotopic protons. These two methyl groups, because these two are same substituents, these two methyls are homotopic. But look at the protons present here. When we look at these two protons, this carbon is having two different substituents like X and Y. So when we replace one of the H with another atom, we will get enantiomers. So these two are called enantiotopic protons. These two are enantiotopic protons. So when they are replaced with a different element, different atom, they become enantiotopic. Okay, right. So generally enantiotopic protons are isochronous, so they will give only single NMR absorption. Now we will look at diastereotopic protons. Diastereotopic groups are non-equivalent and not isochronous, so they have different chemical shifts. That means they will give different signals in the proton NMR as well as carbon 13. The diastereotopic protons split each other with a geminal coupling constants. Because they are not equivalent, they are different, so they will split each other. So diastereotopic protons will give different signals. At the same time, the signals will be split each other. Now, we will take an example, R4 methyl 2-pentanol. When we say they are diastereotopic, for a molecule to be diastereotopic, we generally expect two chiral centers. So if there is already one chiral center in the molecule, then we can expect diastereotopic groups. For example, look at this molecule. So in the previous class, I told you that these two methyl groups are chemically equivalent, so they will give only one signal. Right. Now look at this. When we give the numbering, we will give the numbering like this: 1, 2, 3, 4, 5. So 4 methyl, 2 pentanol. Right. Because there is a chiral center here, methyl, some alkyl, OH and hydrogen. It is a chiral center. So if there are two hydrogens on the same carbon, if there are two same alkyl groups, then they are called diastereotopic groups. So these two protons are diastereotopic, or these two carbons, these two methyls are diastereotopic. How they become diastereotopic? For example, if we replace one of the proton with some other atom, then this carbon, this center becomes chiral, right? This alkyl different, hydrogen. And if we replace one of the hydrogen, it becomes a chiral center. When we have two chiral centers, there is a possibility for diastereotopic isomerism, right? Diastereomerism. So when we replace one of the hydrogen, it becomes diastereotopic. Or when we replace one of the methyl with another group, they become diastereotopic. So this is an example for diastereotopic groups. So these two protons are diastereotopic, or these two methyl groups are diastereotopic. First, we will look at the carbon-13 NMR. Because these two are diastereotopic, they will give different signals. They will give different signals. So altogether, how many signals do we expect in this molecule? 1, 2, 3, 4, 5. And because these two are diastereotopic, this methyl will also give one more signal. So that is why we observe 6 signals in the carbon NMR. I'll just give the values also. So this is 66, 48, 25, 24, 23 and 22. For my convenience, I have written like this, but these are the exact values. Now look at this. This is oxygen attached one. So it is the second carbon. Then these two are next carbon. And this is the fourth carbon. And this is the first carbon. And these two are methyl groups. These two are methyl groups. So this is fifth carbon and this is 5 dash. For example, if I give a numbering 5 dash like this. Because these two are diastereotopic, they don't come, they give different signals. They give different signals for each of them. Now we will look at the proton NMR. Now we will look at the proton NMR. Yeah, here these two methyls. The two methyl groups are diastereotopic. Therefore, they will give two signals in the carbon-13. Now we will look at the proton NMR. In the proton NMR, we get one. There is a proton here. I am supposed to write this. A, B. Yeah, I'll take like this. 2, 3, 4, 5. If it is a chemically equivalent system, we do expect only 5 signals except OH, okay? Or including this 1, 2, 3, 4, 5, 6 signals only. But because it is diastereotopic system, How many signals do we expect? Because it is a diastereotopic system, we expect different signals for these two protons. At the same time, we expect different signals for these two methyl groups also. So altogether, how many signals we expect in the proton NMR? 1, 2, 3, 4, 5, 6, 7, 8. So how many signals we expect here? We expect 8 signals. HA and HB are diastereotopic. They will give different signals. Then two methyl groups, CHE3 and CHE3, they are also diastereotopic. So they will also give two different signals. They will also give two different signals. Now I will try to draw the proton NMR and I will explain this. Highest delta value will be given to OH proton. HC, OH proton we cannot predict because it is variable from 1 to 8. I will try to redraw the multiplets here. This is D, this is OH, this is HA, this is HB. This doublet is for one methyl group and this doublet is for two methyl groups. So this is one doublet, this is one doublet. So altogether 1, 2, 3, 4, 5, 6, 7, 8 signals. So how many signals are there? 8 signals are there. This doublet for one methyl group, this doublet for another methyl group. Now, how do we expect this? See, it is a multiplet, so that is why the intensities are not clear. HC, now look at the HC. Because it is having three carbons, three protons on the alpha carbon, we expect a quartet for this. This quartet is split into doublet of quartet by HA, and that signal is again split by HB. That signal is again split by HB. So we get a multiplet because it is having many lines. So generally it appears like this in the proton NMR. Similarly, look at the HD. HD, because it is having 3 plus 3, 6 alpha protons, it gets accepted. But HD is also split by HA and HB. So it also gives a multiplet. Similarly, look at the HA. I will discuss a little bit more about HA signal. Okay, right. Look at HA. HA is first split by HB. Why? It is one bond coupling. So HA is split by HB into a doublet. So this is JAB. Now this HA is also split by HC. HA is also split by HC. So this is JAC. Similarly, this fellow. Now this HA is also split by D. That means this is further split by D. JAD. JAD. So what is the resultant signal we are getting? 1, 2, 3, 4, 5, 6, 7, 8 lines. How many lines are there? We are getting 8 lines. So this is what is called doublet of doublet. What does it mean? See, this signal is split into doublet, right? This signal, each is split into doublet. So it is doublet of. Now it is again a doublet from this signal, right? It is a doublet from this signal. So it is a doublet of. Then finally it is also a doublet from this. So from the bottom, we come from bottom. Okay? We come from bottom. So it is a doublet of. Then again it is a doublet of. Again it is a doublet of HA. So we expect 8 signals. Now how do we expect these signals? We expect the maximum number of signals, maximum number of lines will be 2 power n. What is n? N is the number of atoms that undergo splitting. Number of atoms involved in splitting. For example, when we look at the HA, we have HB, which is splitting HA. Again, HC is also splitting HA. Again, HD is also splitting HA. Because we have 3 atoms, so 2 power 3, we are getting 8 signals here. We are getting 8 signals here. Here I will give the coupling constant values. Coupling constant between A and B protons is 13.7 Hz. Coupling constant between A and D protons, which is a 3-bond coupling, is 8.3 Hz. Coupling constant between A and C protons, which is a 3-bond coupling, 5.9 Hz. Similarly, these coupling constant values, they also exist for B proton. So we can write the coupling constant values for B proton also. So J AB is again same thing. J BC, J BD. J BC is 8.3 Hz. J BD is 5.9 Hz. Here we are getting 1, 2, 3, 4, 5, 6, 7, 8 lines. Look at this example. It is having a chiral center here. This is citric acid. Because it is having one chiral center, then these protons, they become diastereotopic. There is already one chiral center, so these two protons become diastereotopic. So as a result, we expect 2 different signals for these 2 protons. And is there any coupling by other protons here? No, we don't have alpha protons. These are little bit far away, so we don't expect any coupling here. So in this molecule, we can clearly see the coupling. As we know, these two will split each other, HA and HB, into, they'll split each other into a doublet. It should give 1:1, but we have already discussed about skewing. Because these two are interacting with each other, we expect skewing for these 2 signals. So the internal peaks, they increased their intensity, right? These two, because of skewing effect. Right. Here we can calculate the coupling constant value when we were given frequencies. Just take the difference, right? So the difference is 15.8 Hz. 15.8 8 hedges. So we can measure the coupling constant value. When we measure the coupling constant value, here also, here also it should give the same coupling constant value. Okay, so just take the difference. Here also you will get the same coupling constant because HA is interacting with HB. HA is interacting with HB. So the coupling constant for HA signal or HB signal will be the same. This molecule is achiral. Overall it is achiral, but we have a chirality center, and if there exists one more chirality center, it becomes diastereotopic. Achiral but diastereotopic, hence they will have different signals and will also split each other. I'll give you one more example for this. It is styrene oxide, where we have three different protons, HA, HB and HC. This is styrene oxide. Look at this carbon, it is a chiral center because we have four different groups. So if these two protons, if they are replaced with another group, then this center also becomes chiral. So what we can say, these two HA and HB are also diastereotopic. These two are also diastereotopic. So we expect a coupling between HA and HB. Of course, we expect a coupling between HC and these two protons, but because HA and HB are diastereotopic, we expect a coupling between these two. So when we look at the splitting, HA is split into a doublet by HB, and that doublet is split by HC into a doublet of doublet. First, I'll give the spectrum. So this is for aromatic system 7.3, and this is A, B, C 3.8, 3.1, 2.7. When we look at this, it looks like a simple doublet. But when we take the high resolution instrument, each doublet is split into 4 signals. Each doublet is split into 4 signals. In a low resolution, we do observe only a doublet, but in a high resolution instrument, we can observe each doublet is again split into a doublet. So a doublet of doublet. Now, why it is giving a quartet here or a doublet of doublet? Because HA signal is split into a doublet by HB. Then HA signal is also split into one more doublet by HC. Now we will look at the coupling constant values. See, these two will have a strong coupling. So JAB will be 5.5 hedges, and BC will also have strong coupling, but compared to AB, it will be less. So next highest coupling constant will be observed JBC, and JAC will be having least coupling. Right. Now, how do we see this splitting? For example, take the proton A. Now, proton A is split into a doublet by B proton. Doublet is split into a doublet by B proton. So it is JAB. It is a doublet. Now, again, this doublet is split by HC. HC will also split this into again a doublet. So this is JAC. So these two signals will be split into again a doublet. So altogether we see four signals. Why? Because there are two splitting atoms, so 2 power 2, 4 signals. So it is a doublet of doublet. This is a doublet of this doublet. In a low resolution spectrum, we don't see this. We generally see a doublet. We generally see this doublet because this coupling constant is very low. Or we can also see this like a triplet. We also see this like a triplet. It is possible. Similarly, B proton also. When we look at the B proton, it is split by A proton. Then B proton is again split by C proton. But look at the coupling constant values. AC and BC, they are different, right? BC is larger. So that is why we observe very large separation compared to this. So again, we get 4 signals. So it is a doublet. In a high resolution instrument, we observe this as a doublet or as a triplet, because these two lines, if these two merge together, or if they are very closely spaced, then we don't observe two lines, we observe only one line. So when we observe only one line, because of from these two we observe 1, 2, 3, so triplet. So we observe a doublet of doublet or a triplet. This is not a triplet, it is a multiplet. So this is from aromatic system. It is not a triplet, it is a multiplet.